So today we start talking about energy, and this is a topic from chapter 16 that will not be on the first test. It will be on the second test. And in fact, we're going to be talking about potential energy and a thing called electric potential, which is a new concept. So to do this, we're gonna review a few concepts about energy and potential energy in particular. And let me just try to give you an idea of where this is going. So where we're going with this. So when we talked about force, an electric field, we've done something this semester that's more abstract. So the force on some system, which is some charged object, is equal to the charge of this object in the system times the electric field due to the surroundings. And so, of course, we can calculate the electric field due to the surroundings by measuring the charge on the system and divide by the charge of the system to force. And so the electric field is this is Newton's per Coulomb. So the electric field is really force per unit charge. And by unit charge, we just meant per Coulomb because a Coulomb is the unit of charge, right? So what we're going to be doing with energy here is trying to do the same sort of thing. So what we want with energy, so this is force. With energy, we're going to have the change of electric potential energy for a system is going to depend on the charge of some object that moves, because remember, changes in potential energy had to do with changes in configuration. Things got farther apart or closer together or whatnot, times a change in some quantity called the electric potential. So this is the object that moves. This is change in potential energy, electric potential energy. So this is the charge of the object that moves, and this is called the electric potential. And you can see that it's gonna end up with the same kind of a relationship, that we're gonna have a change in electric potential is going to be, and that's a V, is going to be related to the change of electric potential energy divided by the charge of the thing that moves. So this is going to be really a change in potential energy per unit charge. And that's where we're going with this kind of thing. Now remember that when we talked about forces, we were talking about predicting detailed motion. So force led to a change in momentum, which led to a change in position, that kind of argument. And what we added this semester was the idea that if we knew an electric field, then we could go get forces and momentum changes and position changes. When we talk about energy, remember that energy involved initial and final states. So we were looking of a system. So we were looking at differences in energy between some configuration and some other configuration. And so we're going to be doing that. And we found that if we chose, if we take everything as our system, then we found that the change of kinetic energy of the system plus the change of potential energy of the system was zero. Energy could flow back and forth from kinetic to potential energy. So this is all going to be exactly the same. And so, but what we're going to do is this extra step of having a change of electric potential, which will lead to a change in electric potential energy for a system. So that's the game we're going to play. And we're going to find out that the change in potential energy, in electric potential, is going to actually be related to the electric field along a path. So from the initial position of a moving object to a final position, along some displacement. So it's going to end up being the dot product of the electric field and the displacement. So that's where we're going with this today. Okay, so a brief review of energy concepts. We found that the energy of a single particle was had sort of had two pieces. It had its rest energy, which is entirely due to its having mass, and then it had kinetic energy. And a single particle, there is no potential energy because potential energy is interaction energy. So if we take a system as a single particle, then there's no potential energy for a single particle. And we found that at low speeds, if the speed is much less than the speed of light, the kinetic energy of an object is a half mv squared. And at high speeds, we had to take E equals gamma mc squared, and then K equals gamma mc squared minus the rest energy to get, okay. And mostly for now, we're going to be talking about things going at low speeds, so we can, this kinetic energy of a half mv squared is going to be good enough for us. And remember, of course, that delta means change in. So we're talking about E final minus E initial here, or whatever. So for a single particle system, the change in kinetic energy of a system was just equal to the work done by the surroundings. And we can calculate that because that was just the force by the surroundings times the displacement of the particle in the x direction. So the x component of the force acting on the particle times the x component of the displacement plus the y component of the force times the y component of the displacement plus the z component of the force times the z component of the displacement. And we found, remember, that we could use vector dot product notation for that. So there was vector dot product notation for that. So we could write this as the force by the surroundings dotted into, we called it, might have called it delta R. And in our notation here, we're going to call it delta L. This is displacement of particle. So delta L is the vector. That's a lowercase l, but I write it as a script L because if you just write a sans serif lowercase l, you can't tell that it's not a 1. So it's delta x, delta y, delta z here. So this dot product is fx, fy, fz dot delta x, delta y, delta z. And remember that we had to get a magnitude, and this is a scalar, right? So it ends up, this is a scalar. Energy is a scalar here, although we're using vectors to find this scalar. And the magnitude of F dot force times force dot displacement was the magnitude of the force, the magnitude of the displacement times cosine of the angle between the force and the displacement. Okay. So, and an example of this, a familiar example of this, where we choose a single object as the system, was a ball near the Earth. So ball near Earth. So here's the Earth. Here's our ball. The ball travels upward 1 meter while there is a force by the Earth on the ball downward that's approximately constant. And so there is no potential. The way we've chosen our system, we're choosing the ball as the system. So there is no potential energy because we have a single object as the system. So it's just the change in energy of the ball is equal to the work done by the surroundings, in this case the Earth. And so we have the rest energy of the ball doesn't change. So we have the change in kinetic energy of the ball is the work done by the Earth. And of course, the force is going to be 0 minus mg 0. And the delta y is, so delta, let's write it as delta L, the vector. 0 in the x direction, plus 1 meter in the y direction, 0. And let's say the mass of the ball is 0.5 kilogram. So the change in kinetic energy of the ball is the work done by the surroundings. So this is going to be a 0 times 0 plus a minus mg times 1 plus 0 times 0. And if we plug in numbers, we're going to get a minus 0.5 kilograms. G for 9.8, but for our purposes, we'll call it 10 newtons per kilogram times 1 meter. And so we get a change in kinetic energy of minus 5 joules, and that makes sense because the ball slows down when it's going up. Okay, so the Earth did negative work on the ball because the force was opposite to displacement, and so the ball slowed down. Okay, so that's the so another example would be an electric force acting on something. And so another example would be, suppose we have an electric field in a region that's 1,000, 0, minus 2,000 newtons per coulomb. And we now know how to make an electric field in a region that's actually uniform, right? So that can be, we could be inside a big set of charged plates. And as long as the plates are large compared to the separation between them, we've got an extremely uniform electric field in there. So this is the idea that we can consider a region, legitimately consider a region where we have a uniform constant electric field is actually really helpful in talking about potential in a simple way. And let's suppose we have a displacement of 0 meters in the x direction, minus 4 meters, 5 in the z direction meters, and we have a charge that's 3 nanocoulombs. And you saw from your, one of the reasons you did that lab where you measured the amount of charge on a piece of charge tape approximately was just to get an idea of what ordinary charges are like. And most of you got charges for a piece of tape on the order of something like 1 times 10 to the minus 8th coulombs, so about 10 nanocoulombs, okay? So nanocoulombs is a reasonable kind of charge that you could have on an ordinary object in air. And so the change in kinetic energy of our charged particle here would be the work done by the surroundings. And that would, of course, be the force, which is now Q of the system times E of the surroundings, dot product with the displacement. So we'd get 3 times 10 to the minus 9 coulombs times the electric field, times the displacement, so a dot product with the displacement, 0, negative 4, 5 meters. And so we've got 3 times 10 to the negative 9 coulombs times what? Well, 1,000 times 0 is 0. And 0 times negative 4 is 0. And negative 2,000 times 5 is going to be a negative 10,000. And these are sums, aren't they? So 0 plus a negative 10,000 Newton meters per coulomb, which gives us a negative 3 times 10 to the negative 5th joules. Okay, so the same thing, except that we're just using the electric field to calculate a force here. Okay, so that should be pretty familiar. Now, if we consider systems of more than one particle, systems of many particles, we can have rest energy, we can have kinetic energy, and we can have this interaction energy associated with pairs of interacting particles. So we can have potential energy associated with interactions of pairs of objects. And the way this played out was that the energy principle now looked like this: the change of kinetic energy of our system plus the change of potential energy of the system was going to be equal to work done by the surroundings. And if we choose system everything was common, then that was zero. If negligible surroundings. And delta K system plus delta U system is work done by the surroundings if it's not negligible. And so if we have lots of interacting particles here, we have some charges. They're exerting all sorts of forces on each other. So let's see, that would be attracted to that. Those two repel each other. Those two attract each other. And this whole thing might be moving off in some direction or other. So maybe there's some displacement delta L here. So these internal interactions just change the potential energy of the system. Okay, they don't. So energy can flow back and forth between kinetic energy and potential energy in the system. And the way we wrote this is that the way we got to this, you'll probably remember, is that we said the change in kinetic energy of the system was equal to the work done by the surroundings plus the work done by internal forces, meaning forces that, see these forces here in our diagram, these are internal forces by objects internal to the system. And we said, so we could separate things external and internal to the system, we said we wanted to have everything due to the system on one side of the equation. So we had change of kinetic energy of the system minus work due to internal forces was equal to work done by the surroundings, and it's this quantity that's the change in potential energy of the system. So to come back to our ball example, let's see. So ball and earth, system, everything. So here's the ball, here's the earth. The ball goes up. The force by the earth is down. So we have the change in potential energy of this system is the negative of the work done by internal forces. So that's a minus 0 minus mg 0.010. And so that was a minus 5.5 kilograms times 10 newtons per kilogram times 1 meter. And so we get a plus 5 joules. And so we still, it still comes out right. Delta K of the system plus delta U of the system is 0. This is now a minus 5 joules. That's a plus 5 joules. And it comes out to 0. Okay, so in the electric case, we're going to be talking about, so often in the electric case, we want a system to include all charged objects. So we're going to have the change in kinetic energy of the system plus the change in the electric potential energy of the system is going to be 0 because there's 0 work by the surroundings. In most of the cases, we're going to be considering things are happening quickly enough, particles are moving fast enough or whatnot, that the work by gravity is going to be negligible. Okay, so electric forces are so big that usually in the problems we're considering, the force by gravity is going to be negligible compared to the electric forces. Okay, so we often just won't even be talking about gravitational forces. So let's think, with that preamble, let's think about a situation where we've got a particle moving under the influence of electric forces here. So here's a capacitor, and we know that inside a capacitor, the electric field is uniform throughout that region. And again, the way this capacitor is drawn with the little squiggly things on the ends indicates that these are really big plates that go up to the ceiling and down through the floor. And we're just not drawing the whole thing. We're just zooming in on this little region near the center. And so we have a capacitor here that has a really tiny hole in it. And we have a moving proton that comes in from the left. We don't know how it got moving, but it's moving. And it enters the capacitor and it's still moving. And so we have two locations, A, which is over here near this left positively charged plate, and B, which is closer to the right negatively charged plate. And we're going to think about energy in this situation. So if we choose everything as the system, the proton, the positive plate, the negative plate, the field in between, all this stuff, all charged objects are the system, okay. Then our question is, what happens, what's the best description energetically of what's going to happen to this system? So here's what you said. So you voted for alternative 3 overwhelmingly, which is that the kinetic energy of the system increases and the potential energy of the system decreases, and that is absolutely correct. So how do we think about this? Well, we know that the force on the electron, so here's the electric field. First, we have to think about the direction of the electric field in this region. So the electric field is clearly in that direction. And that means that the force on the proton is going to be in that direction. So it's traveling to the right, it's speeding up because the force is increasing its momentum. And so the kinetic energy of the system is definitely increasing. So that leaves out everything but 3 and 4. So it could be 3, it could be 4, but we also know that change in kinetic energy plus the change in potential energy of the system has to be 0 because there's no significant external forces acting on it. And so, in fact, they can't both increase. So that's not a possibility, and we're left with that answer. Okay? Questions about that? Okay, well, let's consider the same, a similar system that isn't quite identical, because in this system, we have the same capacitor, we have the same field, but now our particle's an electron. Okay, so we still have the electric field pointing in exactly the same direction, but now our particle is an electron. So which of these choices is now correct? And this time you overwhelmingly voted for answer 2, which is correct. And let's see why. So we have exactly the same electric field here. But since the force on the moving particle is equal to QE, and now Q is negative, we have the force on the electron due to this field is actually to the left, but the electron is still coasting to the right, but it will be slowing down because the force is opposite to the momentum, and so it'll actually be slowing it down. And so the kinetic energy of the system decreases, so that rules out everything except 2 and 5. But we know that, again, in the absence of significant external forces, that delta K plus delta U has to add up to 0. So, okay. So here we have a situation where the field is the same, but the force on a proton and the force on an electron in opposite directions. The field is the same, the displacement is the same, but the change in electric potential energy has different signs. So here, when the proton was speeding up, the electric potential energy decreased. When the electron is slowing down, the electric potential energy increased. And what we want is here is something, we have field as force per unit charge. We're looking for something that's potential energy per unit charge. So something that we could just multiply by the charge of the, we want this. We want the change in potential energy is equal to the charge of the moving object times something here. And this something is going to be the same, just like the field is the same. And that thing is obviously going to be electric potential. Okay, so let's see what we what we've got here. So for the proton case, we had the change in electric potential energy was, so we're only working with components in the x direction, so we're just going to worry about x components here. We have so we want the negative of the work due to internal forces. So this is the work, the force on the proton was the charge of the proton times the x component of the electric field. The displacement was delta x, and then we want the negative of that. So what we've got is, we can rewrite that as a plus E times a minus E sub x delta x. So we just move that minus sign over. For the electron, we have the change in electric potential energy was equal to, again, the negative of the internal work, but now the force on the electron, so this is F sub x. The force on the electron is minus E times E sub x because it's an electron. The displacement is still delta x. We need that minus sign. And so we can rearrange this a little bit, and we get a minus E times a minus E sub x delta x. Now why have we rearranged this in this odd way? It's because it turns out that here's the charge, here's what we wanted up above. So here's the charge of the moving object, and here's this quantity, the negative of the x component of the electric field times the displacement, the x component of displacement. And so for the proton, it was speeding up. So delta K of the proton was greater than 0. So change in electric potential energy was less than 0 here. For the electron, it was slowing down. So delta K was less than 0. We should get a positive number for delta U, which we do. So it all comes out right. So it's this quantity, this minus E sub x delta x that comes out being the same. So if we want to write the change in electric potential energy as a particle moves through a field, as a particle moves through a field, change in electric potential energy is going to be the charge of the particle, which could be, in this case, plus E or minus E, times delta V. And so, of course, the change in this electric potential and I'm trying to, I know my handwriting isn't great, but I am trying to make the V look different from the U. So delta V is going to be the change in electric potential energy divided by the charge of a particle that moves. And how did we calculate delta V? So calculate, so this is called, so calculate delta V. Well, in our one-dimensional case, it was just minus E sub x, the x component of the field, times the x component of displacement. In more general case, where we have y components of things, it would be plus a minus E sub y delta y plus a minus E sub z delta z. And of course, if we write that in dot product notation, it's going to be a minus E dot delta L. So this is, what are the units of this? Well, it must have units of joules because that's electric potential energy, coulombs for charge, so it must have units of joules per coulomb. And a joule per coulomb has a name. It's 1 volt. So let's just do an example. Okay. Now this is a general. Let me back up a second. This is a general situation, and so suppose that we can apply it to any situation. So suppose we have a situation where in some region we have an electric field like that, and some particle takes a path starting here at some initial location I and going to some final location F. And so our path actually ran like that. So that would be our delta L. Okay, you'd see that we need both X and Y components in this equation to get the change in potential. So let's just do an example. So an example of change in potential and potential energy. We'll take a really simple case where we've got a horizontal field here. So we'll put location A is going to be minus 0.400 meters, and location B is going to be 0.200 meters. And in this region, we've got an electric field of 500 newtons per coulomb. And we want to consider what's going to happen when a particle moves from A to B. So the first, we're going to divide this problem into 2 steps, though. First, so step 1 is going to be step 1, calculate the change in electric potential along this path. And step 2, multiply by the charge of the particle to get the change in electric potential energy of the system. So here we go. Here's step 1. The change in electric potential energy. The first thing we need to do is we need to get the displacement. So the displacement vector is going to be final minus initial. So it's our final minus our initial. So that's going to be 0.200 meters minus negative 0.400 meters, and that gives us 0.600 meters. Okay. Now we need the change in electric potential. So that's a minus the dot product of the field times the displacement. So this is going to be a minus sign times 500 newtons per coulomb dotted into 0.600 meters. The only non-zero component is the x component. 500 times 0.6 is going to be 300. So delta V is going to equal to a negative 300 volts. Okay, so that's step one. And notice that this doesn't say anything about the sign of the particle traveling this path. This is independent of what particle will travel the path. So just as electric field has a direction that where it doesn't matter what's going to come along to be affected, so a difference in electric potential only depends on the field and the path, and it's independent of whatever particle we might have travel the path. And that's why it's useful. So we got that number. Now we're ready for step two, which is to multiply by the charge of the moving particle. But now we can do two cases. So let's do A. Here's a proton. So we have the change in electric potential energy of the system of the proton plus whatever charges are making that field is going to be a plus E times 300 volts, so it's a Q delta V. And so that's going to be a minus 4.8 times 10 to the negative 17 joules. And does that make sense? Well, if the electric potential, so a proton goes from A to B up here, so here's our proton traveling along from A to B. It's traveling in the direction of the field, so it's clearly speeding up. And so the kinetic energy is increasing, so absolutely the electric potential energy of the system should decrease. So delta U is less than 0, delta K is greater than 0. Let's check it out for an electron. So we have, for an electron, if electron travels along the path, then we'd have the charge of the electron is a minus E, that's our Q, but we still have the same potential difference, 300 volts. And so now we get a plus 4.8 times 10 to the negative 17 joules. Does that make sense? It does, because if the increase in electric potential energy of the system is greater than 0, it says the kinetic energy will decrease, delta K is less than 0. And we see that if an electron is in this region, so we have an electron up here, we've got the force on the electron will be that way, so in fact it will be slowing down, so that all makes total sense. Okay, so let's see if we can practice with this idea a little bit. Okay, so we have a region here where we have a uniform electric field. The electric field is in the minus y direction as shown. We're given locations A, B, and C. What is the difference in electric potential along a path from A to B? Okay. So what is the difference in electric potential along a path from A to B? Remember that delta V equals minus E dot delta L. So overwhelmingly you said answer 1, the difference in electric potential is 0. And that is absolutely correct by the definition of electric potential difference. So here's the calculation we're doing. So we have delta V is equal to, first of all, we need delta L. So delta L is equal to 520 minus meters minus 320 meters, which is equal to 200 meters. And the electric field is equal to 0, negative 400 newtons per coulomb. So the change in electric potential is minus E sub x delta x. So we have 0 times 2. I'll write it this way. A minus 0 times 2 minus E sub y delta y. So that's going to give us a 0 times a negative 400. So EY delta y, and then we have a minus 0 times 0. So indeed, it comes out to 0. Well, you have to, okay, so yeah, so you just pick the non-zero components and multiplied them, but that actually isn't the definition. So you have to be a little bit careful here, right? So let's try a different question. Okay, so same, not quite the same electric field. Electric field is negative 300. So location B is at 220 meters. Location C is at 200 meters. So we're talking about a path from B to C. So this is going to be our delta L, right? It really is helpful to draw diagrams. So the question is, what's the difference in electric potential along this path between B and C? Okay, so the majority, 62%, voted for 6, which is indeed the right answer, and 33% though voted for 5. So we have a sign issue here, which we really need to resolve. And well, you kind of did need it because 6 actually is the answer. So let's see why. So again, part of this is just being a little bit careful, right? So delta L is equal to C minus B, so that's 200 minus 220, which gives us a 0, negative 20 meters. And the electric field is 0, negative 300 newtons per coulomb. So the change in potential is going to be this minus sign times E dot delta L. So we have a minus 0 times 0 in the x direction plus a minus 2 meters times a minus 300 newtons per coulomb in the y direction plus 0 times 0. So we have 3 minus signs, and so we do end up with a negative number, which is a negative 600 joules per coulomb, or a negative 600 volts. So note that when the path, so here's something to just kind of keep in mind that's useful to note. When the path, so the displacement, so delta L, is in the same direction as E, we got a negative potential difference. So our path went from B to C, it went in the minus y direction, the electric field is in the minus y direction, we got a negative potential difference. Okay, let's try another one. This is very similar, the similar picture, the numbers are slightly different. So the electric field is uniform, E sub y is 400 newtons per coulomb. The path again goes from B to C, so that's our delta L. What is the potential difference in this case? Wow, 88% voting. All right. Okay, overwhelmingly your answer is plus 800 volts. That is correct. Let's say why. So again, we have to be careful. So delta L is 0, negative to 0 meters minus 0, 0, 0 meters. So it's 0, negative to 0 meters. E is equal to 0 plus 400, 0 newtons per coulomb. And so the change in electric potential is going to be minus, so EX delta X, so 0 times 0, plus a negative 2, a plus 400 newtons per coulomb times a negative 2 meters plus 0 times 0. So we get a plus 800 joules per coulomb or volts. So notice here that delta L opposite to E, the potential difference is greater than 0. So you can sort of think about it as falling down the direction of the electric field to decrease the potential. You can move against the electric field to increase the potential. And we saw up here at this very first situation here that if this was delta L, if delta L is actually perpendicular to E, then the potential difference is 0. So this is something to keep in mind to just be able to check. So delta L, same direction as E, potential difference is less than 0, delta L opposite to E, potential difference greater than 0, delta L perpendicular to E, potential difference is actually equal to 0. Now, electric field is not always constant, and so we're going to have to deal with that in the future. But in our nice constant situation, these calculations are simple. And we can actually go backwards. So we can find the electric field from delta V. So for constant E, we have, and let's just say it's in the X direction for simplicity. We have delta V is minus E sub x delta x. And remember, this E sub x is a signed component. It's a vector component, so it has a sign. So we just rearrange this. We get E sub x is equal to minus delta V over delta x. Or in the limit, so if we take in the limit as delta x goes to 0, so we take smaller and smaller steps of minus, so E sub x is equal to, really the limit is take smaller and smaller steps, and which we don't have to do if the field is constant, but what we would actually have to do if it wasn't, minus delta V over delta x. We'd get a minus dV dx. And likewise, E sub y is a minus dV dy, and E sub z would be a minus dV dz. And this is technical term, it's called the gradient. So the gradient spatial derivatives. Okay, so what we've done is we've found electric potential. It depends only on the field and the path, the displacement. It doesn't depend on the sign of any charge that might end up traveling that path. And it's useful because the change of electric potential energy of a system is going to be the charge of the moving object times the potential difference along the path along which it moves. Okay, so in chat, your thoughts. What was important? What was the most important idea?